on first principle per kilogram
Yeah.
model.
So how do we make the best out of the sour to knock an extreme enterprise in freeze drying? If we succeed on this year, I mean, we can actually talk about us. So if you want to do a system at your place, at our place too, I still think that's a great thing that if we have, for example, apples here, that'll be relevant immediately, or even things like we get a lot of. Did you ever hear about oleaster? Oleaster. It's another berry, but we got tons of it here, and it just goes to waste. I was wondering, that would be an interesting avenue for juice because it's very tasty actually. Anyway,
I never heard about it. Can you repeat the name again?
yeah, oleaster.
No, it's a berry you mentioned.
Yeah, I'll show you a picture of that. What we have here, and they're actually really good. I mean, they're tasty, and they grow like mad here. Um, yeah, let me show you this one. Can you see this? Does that link work for you?
No, no, it's not working. It's a 404 Google screen.
Try this one. Did that work?
Same situation, same type of screen, 404.
Oh, hold on, hold on. How about this? Is that different?
Yes,
Yeah, it looks like. Doesn't that look like cocoa, right? Looks like cocoa, but it's these tons of berries. They're actually very good taste. They got a typically got a big pit inside, but if you juice it, it's the greatest juice. It tastes like I would say like sweet cranberries. Yeah, taste is actually really good. We got tons of it. It's we started it a long time ago and just self-seeded all over the place, so we could actually harvest tons of it. Like each bush has, I mean, it's just absolutely loaded. And it's interestingly, it would be if we talk about berry pickers, the same kind of berry picker as for blueberries could be relevant to this one. Yeah. Anyway, um, so let's yeah, extreme enterprise, man. Just an update on the complete method. You know, we're struggling with what's the hedgehog concept, the very unique thing that we could be the best in the world at, and that we can score with this program. If we talk about simplifying, well, for the Future Builders Academy, as far as getting people on board, I think that the clarity I'm getting these days, I think it's around extreme enterprise, and that means, um, well, you've got open, collaborative, low cost, replicable, scalable. But I think to focus around the rigor of what's needed to do that, that would mean the 6 month training, 6 months, start your business, make 100K a year. Bam. Financial independence. I think that kind of thinking is good, and then everything around the whole summer supports that. But that's like, I think if we talk about any scaling, any kind of hiring or whatever we got, I mean, all is predicated on a business model working. Because if it's not working, then everyone's going to get fired. You know, so I think the absolute clarity is make sure the enterprise aspect is proven, and we focus that as a very clear message for the whole program. Um, and I think that's a useful framework because I think for you too, like say what we're doing with freeze drying, that's got to have to knock it out of the ballpark in enterprise, right? I mean, that's what we're saying. It's going to knock it out because of the energy costs. So I think that kind of thinking is relevant, and I think you have that already. Um, that it's, I mean, economically, you've got to show the numbers and show it works so it can scale in a massive way. Mm-hmm.
I agree. And it's easier to see a return of investment when there is a 6 months time frame that you can get a lifestyle of 100K per year. It's a really easy just.
Yeah, yeah. So actually, my mentor actually, I'm gonna actually visit him in California for 2 days, and we're gonna just knock it out. So he actually agreed to spend a couple of days with me. So it's going to be, could be the most transformative times of my life here because he is really good. I mean, he is really good. So we'll see what happens there as we go forward. And the latest on the thing is structure the summer in order to get a lot of people, structure it as residencies. And I already mentioned that in an email, but residency where we invite top people and therefore a lot of other people want to show up for that. And I think that's still a good idea. And to that, we're going to add a couple of spring breaks in April, March 14 and March 21st, a couple of spring breaks. That's what we're looking at right now. So that's our program right now, just FYI. Mm-hmm.
When you mention heavy hitters on the email or big people to bring to attract other people, big on their topic of skills and development, can you give me an example to understand better what you mean by that?
What we mean by the idea of attracting heavy hitters?
Yeah, who's a heavy hitter as an example?
So, for example, if we talk about incremental housing, we go up to the guy who's got the TED Talk on incremental housing, Alejandro Aravena from Chile. So invite him if we're talking about incremental housing with a favela construction set or the incremental housing construction set, right? So that's how we want to think about it. So get people who are absolute experts in it. We got to pay a lot of money for it, but the idea would be that it's worth it, worth making it happen, right? Does that make sense?
Yes.
Yeah, and that means you have to have money to do it, but if they're also contributing, like now, for example, Alejandro Aravena, I don't know, like how much he could contribute to AI generated FreeCAD right now, right? But if the person also contributes fundamentally to the development program, that's good. So by that measure, we can say, okay, well, the first ever guy who replicated the compressed earth block press. Well, the earth block press is completely relevant to construction here. Well, invite him, James Slade. You're invited. He's the first replicator from Texas, back in 2010 or something. So people like that who are definitely experienced in a subject matter. And then there's the playoff between, okay, so say James Slade was technically experienced in doing this. He's built his and ran it. But now people don't know about him, right? He's in our crew, our circles. But then there's the other way, get people who are actually well known. Who's a good example of that? If we talk about, I don't actually have any excellent names in mind. Like, I mean, there's TED fellows that I know that are into robotics, like for example, Peter Haas, who's done it, and we talked about open source industrial systems. He's completely into that. But people like that who already have some profile that would act as attractors. That's the idea, and we can actually get very ambitious with that. Talk about anyone who's truly interested or can contribute. Just reach out to them. This is a perfect opportunity, and especially if they're teachers in a residency format, they're on site, but they're actually teaching and practicing with us or developing with us, so they're part of the crew, and also helping me in terms of the teaching load. So that's the way.
Got it.
Mm-hmm. Yep.
Okay.
So yeah, with that said, let me see my screen here. It's giving me this. Okay, let's keep going. I'm gonna put you on this screen here. Okay, go ahead. So let's go into this. Tell me what you'd like to brief me on, and let's go right into. So brief me on what the goal for today is, what we want to accomplish today.
Analyze the formulas to understand the cost components on a granular level.
Okay, cost components on a granular level, so we can consider, just immediately start thinking about, okay, what's a single system look like? What does a big system look like? And the baseline numbers we're looking at, are we talking about 1 million kilograms per year? That's the ultimate goal of waste fruit that's going to get turned into freeze dry. Is that what we've got? Which means if you break that down, that's over 3,000 kilograms of wet fruit per day. Is that about right? Divide a million by 365.
3,000 per day?
Yep.
No, I want to do at
No.
least 20,000 per day
20?
kilograms of fresh. That's like,
Wait a second. So are we still talking in 1 million kilograms per year?
I think that million kilograms per year was of the reference of doing the industrial one that did a total of that amount per year, and the one from for home. That's where you have the reference of that number. Or did I mention I wanted to do it a million per year at some point?
But the figures are actually larger. You're talking about 20,000 per day.
Yes, which is a container full of fruit.
And you have that kind of a load per day, not the whole year, right? Like half the year or something? Or
Not on the same type of fruit. Let's say 6 months can be of citrus, 6 months can be of blueberries. Still, the capacity I want to achieve, it's a full container of fruit, which on average, it's 20,000 fresh kilos.
I like it. And you don't have that, of course, you don't have that blueberry production, but you're forecasting for the future.
Correct.
Okay. So 20,000, that it is. So 20,000, um, then we should look at the extremes. Is there a room that can fit 20,000, a container load? So if you think about a container load, uh, that's in what, crates? Crates of it? Or are you saying basically take that container, just fill it? That's what you're saying? That volume of a container. A
On
20 by, what kind of container? Are you talking about a 20 by 40 or, sorry, an 8, what is it, 8 by 40 or 8 by 20 container? The long one or the short one? Like a,
the it can be both. I mean, for the 20,000 kilos, a short one can fit 20,000 kilos of citrus.
the short
Same,
one, the one that's about 7 meters long, about 20 feet long.
correct.
That can
Yes.
fit about 20,000 kilos, about 20.
Or let's put the big one to
Probably the
have
big one for
for
reference. And we can
uh,
check. I mean,
brief.
check this real quick. I mean, can say I'm gonna ask chat real quick. How
But
many?
the point of this is to make it feasible when
Yeah,
sending from a little further.
yeah. Let's yeah. I mean, let's keep that in mind. So let me ask chat here. How many kilos of grapefruit can fit in a full 8 by 40 container? And it's telling me, oh, shipping container, 8 by 40 container. It's thinking. Uh, I want to. I'm interested in it because I'm thinking already about the walk-in freezer. Mm-hmm. Yeah. So yeah, it's about 30,000 kilos. Right. So yeah, you need like a pretty about nominally that kind of size to begin with. And then we think if that's just filled with it, if we think about a room, that room would have to be several times or multiple times, maybe say like 5 times larger because you've got trays. They're densely packed. So you're thinking about for airflow, how much can you jam pack that? How much airspace do you need between your fruit mass? And I would say nominally, I would say if you shelf it, I'd say like 5 times more room. So say you need a vacuum chamber. So if we start with that premise, if you need a vacuum chamber that's, if it's 8 by 40 feet, let's call it more like several times that. So say 4 times that. So 32 by 40 feet, let's say. Let's ask chat real quick. How many? I'm gonna ask chat. How many kilograms of grapefruit can fit in a 1 cubic meter volume of freeze dryer space? Because that actually gets us the figure for what's the packing fraction. And we're designing right away. Let's do say we do the walk-in, that's going to be one limit, and then we say we do a bunch of little ones, that'll be our other limit. And looking at the extremes is going to help us analyze the situation, and then we can look at, okay, because immediately you can see that, okay, for a big room, well, obviously you've got way simplification on, say, the freezing part if you need one freezer element, right? As opposed to 100 of them, naturally. So the argument you already mentioned in your paper, that if you just have less components to worry about, and the question is, how scalable are those components? Like if one component is X dollars, does it mean that one that can do a big room costs only a few times more, or is it way more expensive? But I suspect that when you scale up those components, they probably end up being much more cost effective on a larger scale. Probably. I don't know, I haven't looked. But let's see, what's our answer? Yeah, so it is saying about 300 kilograms, 200 to 350. So yeah, that factor is about 3 to 5 is exactly what I said. So let's take nominally 4, or even 5. So basically you're talking about a 40 by 40, or in meters that's like 13 by 13 meter room that's 8 feet high, shipping container high. So a walk-in room, that's the ultimate volume you're gonna need. Yeah.
For each
Per day for
for
20,000
dinner, correct?
for a container. You're gonna need a room that's at least as big as that container, and it's gonna be about 4 times as big. When you space out your fruit and you're freezing it, you're sucking the vacuum. Okay, so now tell me, do we have any insight on the per unit costs of vacuum chambers? What's the pressure? Let's just analyze that in low information. So here, I actually want you to take a look at this, not right now, but a book called Primal Intelligence. So I was reading this. Primal Intelligence talks about low information processing. So how you get the insights? I actually think about that. When I analyze problems, I typically do a lot of low information processing, meaning that you look at for the patterns, like the simple things. Don't confuse me with too many spreadsheets. Look at the very basic principles, and we're doing that with like the per unit cost. It's a way to do low information processing as opposed to getting confused on, oh, like these are all the scenarios, blah blah blah. We can readily derive the scenarios from a base unit, and which is our approach. But after this, take a look at, make a note, Primal Intelligence. If you look at that book and it resonates with you, I would definitely read it. Write that down, Primal Intelligence. For me, it's breakthrough. It's an absolutely amazing book. It's about how people think, about logic versus storytelling or intuition. Profound. Okay. With that said, let's talk about the vacuum part, because I suspect that the vacuum part is probably going to be the most expensive aspect. We know you got freezers, right? Walk-in freezers, they're common technology, right? Vacuum
Yes.
chambers are not common tech. I mean, that gets into that's like space age stuff. Vacuum chambers, right?
Would it be possible to get a container as well and adapt it with certain welding works to
Yeah.
work at certain
Oh yeah.
pressure?
Oh yeah. Not a problem. The question is the bottom line to that question, to understand it from a low information context. Yes, of course, you can take a pipe and start welding it up. A thick pipe, like say you take like you can off the shelf get like a half a meter or a meter diameter pipe. You can weld huge flanges on the front and back, and that's your vacuum chamber. It's like making a submarine. But the question becomes, well, what exactly is the thickness of that wall to retain that pressure? So the question becomes, what is the pressure? And therefore, what is the thickness of the wall that we need to make? Now, that's a good question for chat. Let me ask that immediately.
It's 60 at max.
60 what?
I forgot the name of the
unit?
yeah,
Great.
yeah,
That
of pressure.
matters.
60 of pressure. I meant kPa. I think
60
it's
kilopascals?
that's the max it should get after it's already cold, about minus 50 Celsius,
Uh-huh.
that's when you activate the pressure. You get it from 0 to 60 in order to get the ice into a cold trap, and the ice texture in order to make it gas to
Hold on a
put.
second. 0 to 60. 0 to 60 what?
So what I understand the process that when you have it about on minus 50, that when you put some pressure on the tank and you increase it until 60 kPa in order to change the texture of the freeze dried material and be able to make it into gas
Mm-hmm.
to later with the vacuum pump to subtract it from the tank. I believe that's the use of pressure and the max
60
capacity.
kilopascals?
Yes.
That's zero point 0.6 of an atmosphere. That's good news. I thought this was going to be like way low. That's half of the atmosphere, so it's like that's cool. That's not nothing fancy. I was thinking like, oh, is this like semiconductor vacuum? No, far from it. No, it's just so 60 kilopascals. Let's verify that.
Yes, I'm looking at the document that I referenced earlier. And correct, 610 pascals below that.
Wait, now you just said 610.
Pascals or 0.61 kPa.
Okay, hold on a second. So okay, okay, not on a second. You said it's about six. Show me the document. Send me that link. Um, are we in? Let me see if I can find it immediately, which would be under.
I put it in the chat, and I'm gonna do a comment with your email.
Yep. So you mean your latest document? Is that where I'm going?
Yes,
Okay.
the one I just pasted in the chat.
Oh, point. Oh, okay. No, 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 no. We're sorry. Good news is not there. That's pretty low. 600.6 kilopascals to So let's see. I like to think about atmospheres. Oh, so yeah, that's way low. Let me see. So six. Yeah. No, it's way down. So it's less than it's half of a hundredth of an atmosphere. Yeah. Okay. So it's low. So the question becomes, yeah. So we're seeing that, hey, the vacuum chamber, that's pretty significant. Mm-hmm. So you're talking about then we have to start thinking about if we're going to build that vacuum chamber ourselves. How do you do it? What's the baseline there? So we can ask. Did you do any search on chat like what kind of like the basic unit chamber, like what that looks like? Um,
No, I haven't. You mean like a specific measurements?
Yeah, like the cost, like the vacuum chamber cost. Like I asked you, I said, what's like a basic unit of a vacuum chamber that can make a kilogram batch over 24 hours? No insight on that.
No, I didn't get there. I
Okay.
just went into the document, the one I pasted earlier, the one of first principle per kilogram cost model for freeze drying, and there we can find all the different formulas for getting each granular cost and all the components included into that cost category,
Mm-hmm.
but no specific market reference in order to be able to give you the specifications
Okay.
with the prices.
So the simple question is, chat, uh, design a chamber that will go to 600 pascals in a vacuum that is 1 meter in diameter for a freeze dryer. how thick will the walls of steel be in that case? So so that's the question for chat. But let's start looking at the basic parameters of that. Like if we mentioned already that a circular shape is the least amount of material for the kind of strength it would get. That's why submarines are round and things like that, and pressure pipes are round, or pressure vessels are typically round for that reason, because that's the most effective use of material. Now, if you talk about a walk-in, then you're talking about more material, different, less effective in terms of material use, but maybe the walk-in, I don't know about the geometry of I haven't really looked at it, but maybe the way they make a walk-in is still doing a huge tube, but you just walk into that huge tube, because that is the most efficient geometry. So we can ask chat about that. Let's see. So oh, okay, cool. It's only like, it says that for that one meter diameter pressure vessel, it's only a quarter inch. That's not bad. So let's assume that that's like a baseline. So I just if you want to take a look at this, I'll share the chat there with you. But it's telling me that it's, hey, based on the pressure differential from the atmosphere to that low pressure, that 1 meter cylinder is only gonna have to be a quarter inch, like 6 millimeters. That's cool. Take a look at that.
Yes, I'm opening the GPT. So this means in cost.
Yeah, so I mean, steel is $1 a pound. So in cost, so the next question is, how much does a cylinder like that cost or weigh in per meter of length, including the much thicker end caps? So you've got this 6 millimeter shell of a cylinder, but the end caps have to hold all that pressure too, and they're flat, so they're going to have to be much thicker. Probably, my guess is, like, if it's my guess would be like this flat sheet steel, like a couple of centimeters, about an inch. Let's continue asking that. How thick are the end caps? I mean, there's no magic to it. A vacuum chamber is just something that can withhold the pressure, and you've got a port that you can connect a pump to it, so you're pumping out the vacuum. So I mean, no magic. It's basics, but I mean, you're talking about some heavy forces. That's the thing, and you have to seal it. I mean, it has to be openable, right? So opening and closing mechanism, a door, that's airtight. So chat's trying to pump out the weight. Yeah, and as I said, the chat's telling me you got end caps that are flat, exactly as I said, 25 millimeters, which would do it for that level. I'm just doing it like off, just, you know, observing. Like if you see a vacuum chamber, like in pictures or whatever, you see like it's got these fat caps, and yeah, they're thick, like 1 inch or so. But yeah, it happens to be about the right number. So the total weight we've got is mass per kilo.
So the half inch you mentioned, it needs to be the amount of distance.
Half inch?
Or what's the amount that you mentioned earlier
For which distance?
for the material that you're
Yeah,
doing?
materials. So materials, 6 millimeter tube. So that's, get yourself a pipe, 6 millimeters, large pipe, and then you've got yourself the end caps, which are 1 inch flat sheet. So you got this big, heavy, uh, 40 times each slab. So like a per, I think about it in square feet, but per square foot you got about 40 pounds. So the end caps, each end cap's going to be about 400 pounds for that, something like that, I think, because it's about around 3 by 3 feet, about 10 or so feet times 40 pounds. So the end caps are going to be 400 pounds each, so 400, 400, and the chamber itself is, I'm getting numbers like 300 or so. So there you've got like about 1,100 pounds, about half a ton for that container right there. Now, uh, base material cost, if that's plain steel, that's $1 a pound, you're talking about $1,100 for that chamber. Just from first principles, we're not including anything fancy, just the steel weight, and that's the first principle. That's the limit we're at right now. That's for 1 cubic meter, about a cubic meter of volume.
And this calculation is for what size of design for the freeze dryer?
Yeah, so this is just the 1 meter diameter. 1 meter diameter. So about 1 meter diameter, about a meter length. So about it's less than a cubic meter, but around a cubic meter, 3/4 of a cubic meter. Um, 20 plus. Yeah, so that's kind of the basics. Now, um, where do we go from here?
By having this calculation, I just want to understand what's the size of the design that we're talking about, because knowing the size would be an average calculation of how much fruit could be introduced. And after that, we could do the rest of the development of cost calculation.
Yeah, so here we have 1 meter diameter of a pipe, one 1 meter long. But if you have something on a walk-in scale, you're talking much bigger.
And same amount of material.
Wall thickness would change, caps would change. So this is like small. This I think is where the difficulty gets in. Um, so what to do right now? What we might want to do, if you want to start analyzing like a realistic large chamber, you can do it if you have a pipe that's 1 meter. Let's go to, if it's 2 meters high, a diameter, you can start walking into that. That's like starting to be walking scale. So let's take a look at, why don't you, it gets into practical limits, like are you going to be able to find a big pipe from a big industrial manufacturer that's on the scale of 6 meters or larger, sorry, 6 feet or 2 meters or larger? Yes. Question becomes, okay, how much do these things cost? And if they're stainless steel is much more expensive. You can also think about, well, you can also think about coating regular steel to make it food grade. So that's another way to go with regular steel. So different options. But why don't we do this? Let's, I want to ask chat, how do they make the walk-in freezers, walk-in freeze dryers? So why don't you do this? Let's divide this up. So why don't you go and search what is the largest um, steel pipe, because if you don't buy the steel pipe, that means you have to roll that pipe and weld it. So you could do a big sheet of steel like pipe manufacture. That's beyond us, right? Like huge pipe manufacture. That's a little too heavy right now. Let's not go there. Let's go into, if we were to source off the shelf huge pipe, what's the largest thing you could get off the shelf, and how much does it cost per length? Okay, well, can you try that on chat? And what I'll do is I'll start looking at what's walk-in freezer made. How is it made? So I'm going to do that, and you do the pipe. Is that good?
I'm doing just that now. Just
Okay.
one. Steel is the only material that could get the atmosphere pressure into 60.
I mean, yeah, you got steel. Steel is the typical way. I mean, you can get concrete, right? Concrete and steel. You can try that, but let's see, if you've got the concrete pressing on the, if you make a pipe out of concrete, you're talking about that concrete has to be um, not permeable. I think there's other issues to think about there, because if you've got a pipe, you have to be sealed so that air doesn't leak out of it. I'm sure. I think concrete, I mean, that's got air gaps in it, so that wouldn't seal air. You have to coat it with something to seal it from air. So that gets into other things, but we can look into that. Steel comes off right off the top of my head as a feasible thing, but we can also look at concrete. You can search for that. Yeah, okay, so search for what are largest commercially available pipes, and in stainless steel. Okay, and I'm going to search for how is
I found mainly for use for oil and gas,
mm-hmm.
about 610 millimeters or 24 inches. Then I found a bigger one, 60 inches, and 120.
Yeah, for walking, we're looking at more than meter scale, and I'm getting an interesting answer here. They're saying flat. They're saying, I see. Yeah, no, they're saying no. It's not made up of a big pipe. It's made of just like other steel sections.
Does it need to be off the shelf, meaning that it can be made by a welder on contract?
Well, I mean, if you talk about pipe, you're gonna have to roll a sheet of steel and weld it. That's pretty big scale equipment. It's beyond a small shop.
Yes. So the answer is it has to be off the shelf.
I mean, you can do it. You have to then, but then you're adding if it's not off the shelf, you're adding another component of
Agreed.
manufacturing. So let's see what modular vacuum freeze dryer chamber. Okay, so chat's drawing up something pretty cool. Um, huh. So in that doc, I'm pasting the. So go to the very top. So no, they're not. They're not. Ignore what I said about cylinders. Yeah, that would work probably for a smaller structure, but they don't build them that way for large scale. Look at the picture in the dock. Um,
Are you in the freeze drying cost analysis doc?
no, the reference cost temperature pressure outcome. The thing you pasted in the chat. Oh wow. Yeah, so look at that picture. That's you see it?
No, no. Which document again? I cannot see you.
Okay. So this one, I put it in the chat.
Yes.
So yeah, no, forget about the cylinder. That's what the industry standard does, and it's a super reinforced kind of a fat structure, and they scale these up. Okay, great. My question is, how much does that thing weigh for? Okay, so give me one that is say 10 meters long. No, let's do a long one because I think a long one is probably going to be more effective. So do like 20 meters. So we're getting industrial here. 20 meters. I mean, at your scale. Give me one that's 20 meters and 2 meter by 2 meter inside clear volume. So that's like 20 times 4. That's 80 cubic meters. That's bigger than you need. Yeah, that's. Wait, let's see. What is the volume of a. Okay. Um, I'm gonna share that chat. When the chat that I shared with you before, does that update to what I just did in it, or you still see the old one?
It keeps on the old one. You
Oh,
have
it
to
keeps on the old one.
yes.
Okay, so I'm pasting in the chat here in the top. You see the link I'm pasting?
Yes.
Okay, so take a look at that. So a shipping container is about 70 cubic meters. We need about, we said like four of them, 4 times 7, 300 cubic meters. Let's go to the very optimal design, which is 200 cubic meters. This is getting pretty huge. 200 cubic meters for like 1/3. The volume is in fruit. The rest is all airspace, so it can dry. So
What do you mean by optimal design? Are we talking
well,
cost in
no.
airflow?
So I'm like, here I'm saying, okay, this is what we got to build. This is this crazy super reinforced, because the pressure is so low. It's a small fraction of atmospheric pressure. It's way low, like 100th or 1/200th of atmospheric pressure. Pressure on it is huge. So you got this very solid cubic structure that industry standard makes. That's what they do for walk-in freezers. Now, what you'll notice about that freezer is that it's cubic, right? And cubic is the closest you get to spherical, which is the most efficient material use shape. So it's like it's going to be cubic, and it's not going to be elongated, because then it takes more, it's less strong for the unit volume that it can accommodate. So cubic structures, so they basically scale this thing up to crazy. If you elongate this, then the middle is going to collapse. Okay? Then in the middle you have to make like columns or whatever, huge reinforcement through the middle, right? But let's say that's perhaps the easiest way to do it, instead of supersizing this to be like, instead of this being like a whole building, right? So instead of making like a whole building, let's think about, all right, let's get this steel, let's elongate it backwards, put supporting columns in the middle of it so that it doesn't collapse. So I'm just saying, heuristically, I'm just saying, hey, that sounds like a decent idea, because I'm less scared of doing a long dog of this than literally like a building size structure. Because that gets, from fabrication perspective, it's harder to build a huge monolithic structure. It's easier to build something that's smaller and longer, like a trailer, you know. So, but the volume we're talking about for what you need is huge. If a shipping container is 70 cubic meters, 3
You're
times
at
that is 200 cubic meters.
the challenge here on these smaller units would be the more amount of machinery needed, such as pumps.
Um, well, we're not there yet. Yes, I mean, yeah, you have more devices but less structure. So you win heavily on the idea that a small chamber is much easier to build. Just take that pipe with 1/4 inch walls or less for smaller structures, and there you go, you've got it. But here, when
And
you go to the huge size, oh, that gets impossible in the material. So you have to analyze, well, sensitivity wise, cost sensitivity, how much more expensive is it to make more steel than just to add multiple units of the freezing and pressure systems.
that was my question, because if this is even faster to put it in small modules, I think that would be a better return of investment of putting, maybe, yes, having to do automation and material handling, but would be much faster to get in the states needed when the material is inside the freeze dryer. What I mean by this, into preset into -50, put pressure into 60, and then create the product in less hours with these smaller modules. That's why I'm asking how to take that analysis and understand the amount of material used, and the speed that this
Mm-hmm.
fruit is going to become into freeze-dried product.
Yeah, you have to analyze that in detail. So, um, before we, yeah, I get it, and that's one thing at a time. Let's do one step at a time because in all cases you're going to need to understand structure cost. Um, but yes, you have to look at after you get structure and system cost, then you have to talk about time because obviously a big system, because it's so huge, it's going to take forever to pump out or to freeze, whereas small units might be faster. So uh, tell me again, what was the cycle? Do you remember what was the length of the cycles? Point me to that again.
If we're talking about the big commercial ones, it takes about 24 to 36 hours at max. It depends on the type of fruit, but being more realistic on bigger ones, 24 hours. On home scale, 48 hours.
On home scale 48.
Yes. The difference is the commercial ones, they have more efficient way to get into the parameters. They're looking for pressure and for temperature. That's the only difference. The efficiency on get on the specific parameter.
Yeah, yeah. Let's look at those hours again in your hour table. Let's see, 4 hours, 1 hour. Oh, okay. Sublimation is 20 hours. Deep freeze 4 hours. Vacuum pool is 1 hour. Sublimation is 20 hours. Now sublimation. Ah, okay. That probably. So you're noticing that the biggest part is the sublimation part, right?
And that's because of the type of equipment, but there are different strategies. I mean, by designing the equipment ourselves, we can design a more precise and faster system.
But
That, that's
let's assume that at first we're at about the 24-hour rate. Is that fair?
yes, yeah. Just a quick comment.
Mm-hmm.
There are also other strategies that you can like freeze blast the product. So the product needs to get at minus 40 on average, but there are certain machinery that you get a product by it, and it's like a basically freeze blast and puts a product in minus 20. So
Mm-hmm.
that could be another approach to require less time into this first step.
Yeah, yeah. And for now, let's ignore optimization of that. Let's look at the big one, which is sublimation, which takes 4 times as long as the other. So I'm on slide 5 here. Let me show you this. So I'm looking at this here, and just first basic principles here. Heaters, big. That's where it's all sublimating. So you got the vacuum pulled, and then it just starts. So the way to think about it, just low information processing. All right, you got the steps. You freeze it and pull the vacuum. Okay, that's quick. The whole process pretty much relies on the sublimation part, where it's slowly just all that water is sublimating into the and then freezing off on uh, the cold trap or whatever the cold element is. All right. Um, so here's what I'm trying to make a point of. We would be now analyzing, okay, how do you want to design this thing? Given that the vast majority of the time is in that sublimation stage, that gives you a case for, I would say, the larger vessel. But my logic would be if you have a bunch of small vessels, now there's the aspect of loading them. All right, cool. But if you've got a bunch of multiple vessels that you're opening up the door to load, and it's relatively efficient. Maybe it's like the smallest walk-in size as opposed to a huge one. I would say that a small walk-in, you open the door, load it, open the next door, load the next one. I don't see disadvantage of that versus one monolithic chamber. Do you?
All would be on the cost of labor.
Well, I'm saying the cost would be similar. I would say we can. I'm just guessing, but it's the cost appears to be similar because it's not. Say you got a tray that you're rolling in there, you roll it into one container, one place. Uh, but possibly, like we can even be talking about no, we're gonna go into juice it, squeeze it, automate it. That's probably what you want to do. Like I'm seeing, if you tell me, oh, people are gonna be peeling, peeling grapefruit, loading trays. No, I don't think so. Not at your level.
Agree. I want to automate as much as possible.
Yeah, so probably what we got to be designing for right now is we got to stop thinking about walk-in perhaps, because it's probably that it seems like if you've got basically like a ketchup bottle that you're squeezing this thick material onto trays, um, how do you do that? Well, I mean, we'd have to think about it exactly how to do it automatically, but probably we want to stop thinking that you're taking a tray by tray and you're putting, first of all, you're loading each tray, put it in a rack, tray, rack, tray, rack. Probably not. You want to probably automate that somehow. Then, or even have some internal mechanism where you're just squeezing that stuff into all the trays or something like that. Like like a gutter system that flows from one tray to the next, right? And it just overflows and fills the whole thing. Turn it on, fills it, it floats from one to the next. Hey, that's what I did. Let me show you one thing. That's that's how we did the watering for the aquaponics. You fill. Let's actually discuss this as a good metaphor. So for the aquaponic greenhouse, because this might be relevant. It's funny. Kind of cross-fertilizing this with aquaponic greenhouse experience. I want to show you what I did there. Let me see. Let's see, probably automation or whatever. Aquaponics.
I will take a look on the limits of pressure and temperature for each product in order to understand if this system, if it's increased on pressure as an example or temperature, could be do it in a faster way. Because talking about the gravity and using the juice as an input, I'm just wondering how to make the full automation in order to be able to make it happen as fast as possible. Because gravity, how slow could it go to keep hours in a certain stage, as an example, deep freeze, and then go into vacuum fill, and then go into sublimation. I just wondering about the limits in order to process it faster.
I think you probably stop thinking about faster if it's automated. So because okay, if the labor part is that's the part that's loading and unloading. That's upfront. The whole process there, I don't think labor is needed there. So I would think about it probably. The loading would probably be a non-issue. Like you're saying, you think it would be super important to get that in there as fast as possible.
No, just the timing of how to do it automated by juice. I haven't understood yet the properties of the fruit. Example, if we do citrus, it's going to be the peel and it's going to be the juice.
Okay,
It's
let me
going
show.
We're pleased to announce our
yes,
second open source.
Uh, let me show you something on. I just want to show you how we did it here. Um, okay, I'm gonna let me share my screen. Okay, let's talk about that. Let me share my screen just for a second. I want to show you what we did because this is a once again a metaphor. Okay, so do you see my screen? Where did that go? Take a look at this. So these are trays. So this is your fruit trays. Not these are hazelnuts here, but each tray is watered from the bottom, and you see the hoses there. So you're filling it up each tray, and you see me pointing
I do, yes.
there. There's you can't really see it, but there's a spout that goes down once the top tray fills up. So you fill this one, you fill the middle one, and then you fill the bottom, and it goes back into the ponds. But it's all automated. All you need to do there is just turn on the pump. That's all. So that is an example of like as long as the thing is, as long as whatever you're pumping in there flows, and say you want to do juice, well, juice obviously flows. We're probably reserving the possibility of pulp, right? Pulp, which is, in which case you've got freeze-dried fruit powder, right, as opposed to freeze-dried fruit juice. Is that right now we don't know which we want to do we?
I would say powder. It has the most market now. But even if it's juice, it's gonna be freeze dried, so the water's gonna be taken away. And it can be turned into powder.
Yeah, I'm not getting the distinction because both are going to be powder. The from the whole fruits, it's going to be, I mean, powder with more other stuff in it. For the juice, it's going to be a more pure powder. But they're both going to be powders, right?
Yes, the end output, it's powder, correct?
Right. And you want the version when you say which one do you want, right? Because that would kind of like our shift thinking would have to shift. In one case, it might not be able to flow. Like for very thick fruits, it would not flow. But if you juice it, it will flow. Right? Is the market where for the juices that are powdered, like the price is much lower, or it's similar?
I understand it's similar. It's just how you do the input of the fresh product. You could put it on slices or you could put it into a liquid form as a juice. What I meant by speeds earlier is that when you juice it, you're going to have different properties. One is the part of the liquid, which is in juice. The other is the pulp, and the other is the peel. When you put it on a process, now that these are separate, I was wondering about the limits, how fast this is going to do the freeze drying compared to doing in a conventional way, which is the whole fruit or just the sliced fruit.
Uh, because juice is going to have much less surface area exposed, it's probably going to take longer. I don't know. I don't know without looking at that. But we can
Meaning, I'll study that.
now. It probably we can probably like mechanically in terms of automated loading. If you're gonna flow the pulp that doesn't flow so well, that'll be a different design. But I'm sure you can automate how it's loaded. If it's not liquid, it's harder. We would have to compare at the stage when we're actually looking at automation of loading. We have to take a look at what are the details of each pattern. Like how do you have to design the trays to allow that to flow versus where it's in juice versus in a more chunky form. So I have no idea about that right now. I can't comment on it. Um, But we were discussing the idea of when we are, the biggest part is still the sublimation part. So you can freeze it, yes. You can pump the vacuum, no problem. The sublimation part is the time consuming part. Now, yes, it's less surface area because you got liquid, but I can't tell just without looking into that. But let's ask that question. That's pretty important right now because if um, I mean if the prices are comparable and the process is similar, then we would go for the easier way to do it. Now there's probably a quality hit with juicing because juicing is not, is juice still called whole food? Um, I mean one way is, you see what I'm saying? Juice is not whole foods anymore.
Well, it depends on the final formula. You could do the juice and then you can add the pulp and the peel and
There
put
we
it
go.
in a product. And that's whole fruit. It's just the input form you're changing for efficiency, not
Ah,
for quality purposes.
so right now I would say go to juice it and recombine it.
Yes.
I mean, I'm telling you, for if you want automation, juice is the way to go. It's obvious.
On citrus, yes. Blueberries, probably. I mean,
But
the
why not?
blueberry.
Why not? You recombine all the fiber and all the pulp stuff later. Like it'll, what percentage? What percentage is water is blueberries?
Similar, like 90%.
Well, why are you saying it would be so different then?
I meant the need to create different processes and then need to put them together. On the blueberry, there's no need to use it just to spike part of the skin. So the output of air and water content is faster from the fruit because the skin tends to make it hard if you don't do a hole in it to do the freeze dry process.
I didn't follow it. So you're saying that? Let me see if I get this. With the blueberries, what's the? No, I don't get it. What's the idea there?
As a whole fruit, you just need to pinch a hole into each fruit. That
Ah,
can be with a machinery that can do multiple.
okay,
So
that's easy. I see. I
the,
see.
the water goes out and you can freeze dry it efficiently.
Do you know how? So when they freeze dry blueberries, do they then powder them at the end?
Yes, I understand that the form at the end of the freeze drying process, it's not necessarily a powder. It's like a certain structure that you can blend, and during that blend, it's powdered.
But the blueberries themselves, they remain as like you can see that they're individual chunks, or no? They pretty much fall apart.
Almost fall apart, like glassy.
Okay. Okay. Yeah. Cool. Okay, but I'm seeing that juice it. That's it. I think we should be thinking juice it and recombine it from process control point of view.
Sure,
Let's
if it's
assume
not,
that. So I would say that's, we can knock that out of the ballpark. If you're now going to insert a tube into that vacuum chamber, whether it's like, simplest thing would be there's a tube inside there. You turn on the fluid, load it up, done. No people.
okay.
Saves brutal work. I mean, you don't want people to be spending their entire day loading trays. That's dehumanizing work, right?
Yes, there are better ways to spend time for sure.
I mean, from moral intelligence perspective, I mean, that's not a good job to create. Does somebody enjoy doing that 24/7, day out, day in and day out? No, I think that's human punishment, right? For
Pro-
people
pro-
that don't have better things to do. That's for people that don't have options and they have to do that for a living.
Yes, correct.
Right. So you want to avoid that. So that's an ethical way to do it, I would say.
Agree.
So, okay, automated, absolutely. I don't know why people are talking about labor. We've got robots these days. So anyway, I mean, I think it's kind of older thinking. It's like there's absolutely no sense if to be doing that manually. If you're doing it yourself, yeah, I mean, because those systems cost, but once you implement a pump, you can load up an entire village of trays with a single pump, right? So that becomes cheap.
What would be a good next step? So we have the information where to focus on. We're talking about automation using doing three different crops for this exercise of building the freeze dryer open source.
Because this goes to why I'm getting into all of this, because if we assume automation that's going to tell you what form factor you'd want, then I would completely stay away from a big walk-in chamber. Unless we need to do that, but I mean, you have to unload it still. Like, how are you? Okay, so we just addressed the loading part. Now we have to think about unloading. But what I'm saying is, this leads us to insight into how we're going to design the system. Because if we can, now we say that we are going to automate that, then we no longer need the large chambers where you walk in. It could be a long tube, for example, right? But then the second question would be, at the end of the process, you have to open it up and get those things out of there too, right? So how do you do that? But what I'm saying is that right now we're focusing the discussion to how we want to go about it to make it practical. But we're just discovering that with automated juicing, like that loading part, there's no case for a large chamber. We can go very small, which informs how we're going to design the chamber. And that means low cost. Like if it's a much smaller chamber, much lower cost. Because it's much harder to, if you're going to do a little pipe of vacuum, it's the pipe that does this is probably less expensive than a bigger pipe that can do twice as much. And that scaling is favorable towards lower scale, because as we said, like they don't even make pipes that big at the kind of scale where you go into walk-in size. It's just ridiculously expensive, and therefore they're actually ending up doing the square structures. But what I'm saying is that there's a tendency now, from what insights we're getting, to say, okay, we can do smaller vessels, and that'll be perfectly fine in a more modular system. We don't have to have a monolithic one. But we're still exploring that. After we discuss the loading part, okay, we're just trying to reason out from kind of like first principles how we're going to design this. But we have to address, okay, so do we see a clear way? Now we see a clear way to load. Okay, turn on a pump and use our aquaponics feed-through system, kind of system. How are we going to unload this? So now it's this powder. Okay, that we have to address. So now it's not flowing anymore. What do we do? So that is a real issue. And do we basically end up at the same place? That means, oh, you still need this walk-in thing or whatever. How do we think about that? Yeah, I guess that's the loading part is the easy part. The unloading is the hard part, I think. But already we've saved 50% labor, so we're still good. Well, we still more than 50, because for loading it's probably more. We probably saved more than 50% of the labor at this point, but let's say around 50. We got to address unloading. So do we see any way other than you taking out trays one by one? How do you automate that? I don't have a clear answer for that. So this kind of gets us back to the initial analysis problem, the initial sensitivity analysis problem. So that, I think, let's ask chat, like, to move along with the sensitivity analysis. What percentage of the cost is structural only versus logistics? Let's just ask that question. So I'm gonna just ask real quick. I was asking it about the. Let's still ask it if we do go with the one that's like in our document. Let's still ask chat, like, for the equivalent volume, which is 200 cubic meters. 4 times. It's going to be 50 meters long. Well, that's huge. Let's cost it out first. So let's just get like baseline costs of how much this would be, and compare whether a long dog, one that's super long, would be lower cost than a big monolithic one. Because maybe it's true that it's no, the big monolithic actually ends up being much more cost effective, because it is a better way to use materials, but that material has to be thicker because you've got a larger structure. So I don't know the answer to that. So let's just ask. Go ahead.
What physical properties would you measure in order to understand what do we need? By this example, a grapefruit, I can grab 1 or 10 grapefruits and use them, and then understand the properties, how is the context of the texture, and from there we can get a better idea on what we're talking about regarding we have this material, certain parties on use, certain parties on peel structure, take the sizes, take the weight measurements,
Mm-hmm.
and from there we have a more clear example on the physical properties of what we're talking about. And then we can calculate that material, how we would move it when it's fresh, and after it's freeze dried, it's going to have a different property.
Mm-hmm.
We're talking like a glassy with a different weight.
Mm-hmm.
By that, it's going to give us a more clear example of what we really need on the automation part for getting out that glassy texture material after freeze dried.
So your point is you want to do that before going anywhere else, or that's something you're saying you can do, or what are you saying?
The point is, how do we calculate after having that information?
Well, I mean, so at this point we just said, okay, if we're trying to look at what actual sizes of devices we need, and we're just doing like first approximation. We're saying if we've got effectively a container, the volume of the machine itself will probably be several times that container. That's like a first hand waving assumption. So we went with that. Are you saying you'd like to get more specific on that? That, oh well, maybe after seeing the reality of how much juice there is, maybe that volume is actually much better? Is that kind of what you're saying? In other words, we need to go to a much smaller machine.
I was just thinking loud. I can make it any form. I'm okay with. I was thinking loud about maybe how to be more granular, specifically
Yeah.
focus on the material reality.
Focus on the material reality. To
On the
do.
automation, so we went from physical fresh fruit into making it juice. What's the different context of a fruit that is made juice? It has different materials, textures. That's what I meant. But let's go to step one. I would say I'll complete the formulas. I'm talking about cost, and maybe later worry about this texture and physical properties.
Yeah. Um, I want to ask chat, how much would a structure, would a vacuum chamber to handle uh, 20 tons? You said 20 tons, right?
Yes, of fresh fruit.
Of fresh fruit. And how much would it weigh? Because I always ask the weight because we know the price of steel, and if it tells me one number that says, oh, it's going to cost $1 million to do this structure, my first checkpoint to see how reasonable that figure is, well, how much does it weigh? Is it going to be like $1 a pound, or is it going to be more like $10 a pound? Because if it's like $10 a pound, that means all that went into fabrication labor and other costs outside of the steel. Just like roughly in terms of first principles. So what's the answer that it gives us? Um, yeah, per batch. Yeah, it's telling me about 100 cubic meter chamber. I said 200, so we're roughly. But at higher density, it could be as little as about 60 cubic meters. So it's telling me about 80 meter cube chamber. So yeah, it's saying that no, we actually don't need way more space than a shipping container. It's about a shipping container size, so 80 cubic meters. It's saying, and the cost is yeah, carbon steel, 500,000. Food grade stainless, about 1 million. All stainless, like about 2 million. So that's what they're saying. Now, how much does this weigh? Stainless. It's telling me about like 20 tons of material. 20 tons is 20,000 pounds. So do you see the disconnect there? So the material itself, if it's largely carbon steel, the materials themselves are only $20,000. It's telling me the price is going to be $1 million or $2 million. So there's like, you see this thing? So it's saying it's like way more expensive than the material that goes into it. In other words, if we were to do it, you'd hire your welders to build it for you, because this is ridiculously out of control cost. It's like 10x for than a price of 10 or 20, 30x than the cost of the steel itself. So that's just a quick check that, yeah, okay,
Yeah.
so you're going to end up paying like $1 million for it. No, it's like the materials in there are only 20 tons. So 20 tons should cost you much less than that. 20 tons is 20, say 40,000 pounds. So $40,000 in materials. That's a reasonable figure. That's like, okay, yeah, we could build a monolithic chamber like that. 40,000 for processing that much. That's a huge volume. Um, so that's reasonable. Now, yeah, okay, so that's some baselines. So if we believe that, then what we're seeing here, hey, the vacuum chamber is quite doable. It's not it's not this esoteric thing like a huge pipe, which could be difficult to source. This is just like regular sections of steel, so just a lot of cutting and welding, or if you get the right stock, mostly welding. So that's where we're at. But we have to compare that to the cost of all the systems. So for the systems, you got vacuum pumps, you've got the freezer parts. The thing about, so for sensitivity analysis, just the only consideration is if you're doing freezing and vacuum pooling, if you have multiple chambers, at least for the vacuum, you can connect one chamber at a time, so one pump could service everything. You see that? Because vacuum pumping is only 1 hour of the 24 hours, you can service 20 of those vessels with one pump.
Yes.
The freezer part, likewise, we can take the freezer part because it only takes X hours, like 4 hours, can potentially share that between like 6 individual chambers. Now in yeah, so now you have to get down to, and then the sublimation part, that's easy because that's just heater elements, that's cheap. Okay, so we like cost wise, okay, that's not going to be a huge difference between a bunch of individual chambers versus a big one. So for the sensitivity analysis now, you'd have to look at what are the specific components that we're getting, how much, like for example, how big a freezer element, freezer compressor do you need to serve this entire volume, and take a look at the cost of that. What would it cost for one big device versus say like 40 little ones, or 10? What do we want to say for the multiple small ones? Like we want to analyze the one cubic meter versus 40 cubic at the, no, 1 kilo versus 40 kilo final, because those are still way smaller than what you're seeing we need. So do we want to go with the extreme one versus like 100 of the small ones or something? Like how should we do that? We're saying you need a shipping container sized one.
Yes, but I think these are two different ways of comparing. We can go what the market already has, like the home freeze dryer takes 30 pounds of fresh market,
Mm-hmm.
and cost about 7,000 US dollars.
Mm-hmm.
And the commercial freeze dryer can take 1,200 pounds, 1,200, and that costs 700,000 US dollars.
Mm-hmm.
So we can take that comparison and then do the cost calculation and make a similar requirement in fresh pounds, 30 and 1,200, for comparing building our own or in modular way, or building in bigger scale, just to have the commercial comparisons and also the build your own on the different models.
Okay. So what would you suggest as the next step would be?
Just what I told. I'm gonna keep working on the cost formulas just to define each component, and after that, I'm gonna do the different comparisons, included the same amount of fresh pounds, the the 30 pounds and the 1,200 pounds. But with the information I got from the cost calculation of first principles.
So how are you going to be able to break? Are you going to be able to break down the price of each machine by component?
Correct.
How do you do that?
You explain me later the amount of volume you get and how much space you need. Then you explain me the amount of material needed and how much space does it need. And by that, we can get a cost of the material of steel, as an example. Then I can get cost of different pumps, heaters. That's what I'm thinking on doing.
Yeah. Yeah. Exactly. Yep.
And just if you click on the first message I sent on the first principle per kilogram cost model for freeze drying, that's where I have the exact formulas, how I plan to be filling the information in order to have a really precise granular per component analysis. So,
Okay. Okay. That. Okay.
and if you see something amazing, please let me know. This is something I research. I use the chats as well and input different information, and also your email's information in order to make something as specific as possible.
Okay. So something like a table of. Let me see. Energies. You'll continue working in this document.
Yeah, which are basically the cost buckets of each component and process that I'm gonna do per kilogram of freeze-dried product. So the labor, each part of the labor, preparation, pre-treatment, load and unload. I'm gonna take it on freeze-dried 1 kilogram output cost reference.
How are you going to identify the actual components? You're going to say, you're going to look at, um, like for example, because we, in the actual specifications of the different machines, does it actually say which components they use? Like what's the pump that they use? Like for example, vacuum pump. Tells you.
Correct. So if you go into the Harvest Right or Tech Source
Mm-hmm.
pulse, you open their technical data sheet.
Mm-hmm.
They tell you which pumps, which are electric, which use oil, what is the power that they use, and capacity.
Okay.
So for is going that route. That's why I mentioned the commercial freeze dryer, because I want to be able to compare what already exists and then doing it, building ourselves or open source. That's a first comparison. And the second one would be doing the improvements of automation using and different material usage in order to make it much better.
Yeah. Um, so I can see how you can get the price, the exact prices of the components, the active components, but what about for the vacuum chamber? You're gonna do the kind of calculations we did today, just now, to
But
estimate, because they're not gonna tell you like those specs. You're gonna basically say, oh, okay, well this machine weighs so much and therefore it's got so much in steel structure. So that's how you will.
I'm gonna try to reverse engineer, yes, from there.
Mm-hmm.
But I would get, an example would be taking the material structures that you gave me. I mean the amounts per volume, and do a side by side comparison as if the commercial had the same amount.
Yeah. Okay, this is good. And your end product is there. You're gonna get like a price structure. What's end product? The price structure per kilogram produced. And from there, are you trying to simply extrapolate what our cost would be? No, you're just getting this is the commercial grade cost, what we can do. And on the other side is, okay, here's what we think we can do with open source, right?
Doing the same, but just open source. And
Yeah.
then after that, what I really want to achieve is doing the optimizations to making it open source, but much more efficient. It can be modular, it can be monolithic, but that would be after just having the reference of what already works on the market. What could we do the same but open source? And after that, do the optimizations to automate the most and make it the most cost effective per freeze dried kilogram.
I like it. Um, yep. And tell me more about returning back to some of the former steps where you're going at the step of validating the electricity part. Is that something that follows this economic analysis? So after you get that, you make a decision on which system you do, whether you buy it, you make it, or whatever, or are you still just going to buy the commercial one?
No, I want to make it myself because as we see the big difference of home one with 30 pounds, 7,000 USD, and 1,200 pounds commercial one, 700,000 USD. So the economies of scale just it's too long to get the return of investment back and to scale. Like if I want to do production of many fresh kilos, that would take a lot of $1 million.
Mm-hmm.
In case of us that we can build it, it's gonna be a game changer in order in, instead of doing 700,000 per 1,200 pounds, we can do much, much less. How much? I don't know yet.
10x.
At least, yes.
Um, so you're not doing the energy analysis until you make your own. Is that what we're seeing here?
Well, I can make the energy analysis. I can buy a home size one just to be moving forward with the energy analysis and also having some samples of the final product. Yes, but buying a commercial one, I don't see that's going to be the route for scaling. So the energy, yes, it's something I want to do as soon as it's needed. I just meant when scaling.
Okay.
Do I?
So
Yes,
you're thinking of just getting the 1 kilogram product one and testing the energy aspect on it?
yes. For me, the energy part is still very important.
Yeah. And what are the possible forks there? Can there be a failure there, like energy doesn't work? And what would happen there?
I wouldn't say that would be a deal breaker. It just would have to be based on how much optimization on cost it's going to be on the future freeze dryer. So yeah, maybe we have to connect to the grid. But if we're talking of big freeze dryer at 1/10 of the cost, and we're talking the return of investment because of the capital expenditure is going to be much less, that still could make a lot of sense.
But hold on, we how does that agree with the idea that the largest part of the cost is energy? Like what we say was, what's part of it is energy, like 90%. What were those numbers?
If we don't take into account the cost of investing into a freeze dryer. So when I used to say that energy was like 80%, I wasn't taking into the full cost accounting the depreciation of depreciates and the cost of buying a freeze dryer.
Okay, so what is that number then when you do include it?
It's about 30%.
30% for energy?
Yes, but as I mentioned, so there are the ongoing costs and there are the full accounting costs. That's why I mentioned when something depreciates and the cost of purchasing something. So it's not day to day. If you see your full receipt of your monthly ongoing cost that depreciate, it's part of an accounting cost that you decide to do it in a certain amount of years. The the ongoing cost of what you get of water, electricity, labor, that's what I meant. That electricity, it's about 80% of that. Water, labor, and electricity.
If you do full cost accounting, including capex depreciation, then it's 30% for electricity.
If you do the full accounting per kilogram of freeze-dried product, yes, with full accounting.
Um, you responded the way you responded. Is there another way to account that is not 30%?
I cannot answer that because I don't know. I saw this from the advisor that is,
So full cost, bottom line, full cost accounting, energy, 30% per kilo of product.
yes, but that's on machinery that cost 700
Yes, that's using industry standards. Let's think.
until
Let's think about that for a second. If the machinery is 1/10 the cost now, how does that change that? Um, if it was 80% without capex, but 30% with, then that number goes largely towards energy costs, like maybe 80%. I'm just trying to think through this. So if you got a free machine, let's assume that we got near zero marginal cost for capex, which is not the case, but I mean, let's do an extreme limit. If we do achieve that, your costs are 80% energy. In that case, don't you have to have PV to make this successful? Because you said no, this is still a go, even if the electricity doesn't work?
Because of the price of output product of freeze-dried powder, and that you invested much less money because you could build your own, it's still a profitable business in less time. So if we compare it to commercial price, it would take about 5 years as an example. If you build it yourself and you don't have the big cost of acquiring one, you can get back that money on first year, second year. So does it make it more attractive? Of course.
Okay. Because it's still profitable whether you have free electricity or not. Otherwise, people wouldn't be making this, making freeze-dried fruit powders.
Yeah, more time attractive, for sure. Not near zero marginal cost, no, but much more attractive to put your money into a vehicle like this than to put it on this same vehicle and wait 4 more years.
Okay. So, with that logic, then the energy testing, does that mean that's a secondary thing, or how would you weigh the importance of energy costs now versus getting the capex on the machine to very low? How
Yeah,
how do you think about that?
I would say energy is still number one because we don't even know if we can take the machinery and automate it now. But we know that there's an energy system that can be proven and make the current machinery much more efficient.
Mm-hmm.
So number one, energy. Number two, build our own.
Yeah, yeah, very good. I did you see that I redid the cost per kilowatt hour? Did I send you that?
No,
Take a look at this. I redid that, and it's better than ever, actually. I did it based on the kind of system we're installing here and over the next month. Yeah, there's a new page called Zero Marginal Energy Cost.
I think I saw it on the wiki.
Yeah,
You updated most of it.
yeah, but you see what's at the end there. So the inverters, I mean, it's already great. Open source inverters get that cost down half because the inverters is such a, it will break after 10, 15 years, and but the PV itself and the inverters costs more than the PV. The PV itself is 25, 30 years. So yeah, anyway, I'm just saying the news is even better if you got open source inverters. PV costs half a cent per kilowatt hour. That's just so beautiful.
It is.
Yeah.
But again, energy number one priority.
Okay.
Still,
No, this is good. Good. You're doing some good work on getting the numbers shaken down for the. I mean, you're spending some time on that document, so that's pretty good. You're basically pouring through the economics of that. So you're doing the full economic analysis. So next time, let's talk about if you can get down to the per kilogram for each system. hmm That's good. Good work. We're moving along.
we're moving along for sure. So
hmm
I will keep working on information and let's see when we can talk again in a
Yeah.
week. Sure.
Yeah.
Yes.
Yeah. Yeah. Just let me know. As soon as you got some stuff, let's set up the next call then. That sounds good. I'm going to be travel. Well, actually, so yeah, next week works. I'm not going to be here Monday, Tuesday, visiting with mentor. So yeah, after that.
We can do after that for
That
sure.
sounds good. Sounds good. All
Thank you,
right.
Marcin.
All right. Thank you.
See you
That's
soon.
good work. We'll talk soon.
Success.
Bye bye.